Okay, so now we have Ulrich Sperhake from Cambridge University, and it's going to talk about gravitational waves from boson stars and their potential signature in LIGO observations. So, Ulrich, it's your microphone. Yeah, let's see how this works.
Okay. Well, thank you very much. And thanks for Luis in particular and the organizers for giving me the opportunity. It's a pleasure to be, it's always a pleasure to be here, but trust me, in November, if you are based in Cambridge, it's a particular pleasure. It's really wonderful. And those who've been with us yesterday, they can easily understand what a invigorating effect this has had on my health, which was severely strained by recent admin activities beyond my delight. Anyway, so let's move on to the science. The purpose of this talk is to check what actually we might be able to tell from LIGO observations of compact objects as far as the nature of their source is concerned. This is work I've done together with Tamara Evstafieva, Michalis Agathos, and Isabel Romero Shaw. And in particular, Tamara deserves a lot of the credit for the work here, which she's done mostly in the final year of her PhD. But we laid a lot of the foundations actually in previous work that I did with Tamara. So this is work that got recently published in PRL, and if you're interested in some of the more technical details that sort of lay the foundation for our numerics, it's summarized in these papers here. Um, so thanks to Dario and others, I can save a little bit of time in telling you what boson stars are. Normally, especially when I have a more astrophysically minded audience, the term boson star raises more laughter than interest. But here, I fortunately have a much more open-minded audience. So I will still say a few things, just in case, for those of you who are not working with boson stars directly, it might not be a bad thing to get a bit of the rough idea of what they are. The idea goes back to John Wheeler's attempt to compute self-gravitating compact objects composed of electromagnetic fields. Now, at first glance, you may think that sounds really weird, but we are obviously guided a lot by our experience that all stars we know are made of fermions, like the sun. Well, the Earth is not a star, but it's made of fermions, neutron stars, and so on. But of course, it's a perfectly sensible question to try and think what, how could we construct equally or similar objects out of bosons? And the most natural boson is the electromagnetic field, it's a photon. Unfortunately, this didn't work. There are no equilibrium solutions if the matter field you're considering is the electromagnetic field. Now, I don't know whether there's a proof for this or whether nobody has ever found any models, but for our purposes, the key point is actually that John Wheeler's idea motivated people to look at other fields, more hypothetical fields, and that led to the idea of boson stars. So the candidate fields we're considering here are QCD axions, axion-like particles, dark photons. But my perspective is always a comparatively agnostic one. I don't particularly care at this point whether boson stars exist, what exactly they're made of. For me, they are a proxy for anything that's not a black hole in GR. And I will explain during the talk why I think they're actually almost perfect proxies. So the, the the idea behind the boson stars I'm interested in this talk uh, is a complex scalar field. Now there you can generalize this following work by Carlos and others that to spin one fields. Then you get Broca stars, which from a global perspective have similar properties, not identical ones, but similar. And they were actually discovered a long time ago. This is over 50 years ago. Shit, because I was born around that time. Anyway, so As you have actually seen here at this conference, there's a whole zoo of boson stars. There are the Broca stars with spin 1 fields, L boson stars that Daria has mentioned, multi-oscillating boson stars, thin shell boson stars, solitonic boson stars. They are variations in the potential. I will focus on a class called solitonic boson stars made of a single scalar field. You know, I like it simple because I'm not good enough to do hard things. So the formalism is comparatively simple. So you take the action for a single scalar field, you make it complex, the bars, the complex conjugate, and well, then you use the covariance principle to get the general relativistic action, and that immediately gives you the energy momentum tensor. You have the Einstein equations and plug that in. There is one free function here, that's the potential function. The simplest case is that it's a massive field. For massless scalar fields, you don't get boson stars. So you need at least to have a mass term in the potential. But if you do not allow for self-interaction terms, you get what is called mini boson stars, hence subscript min. A common generalization of that is called, for reasons I'm not really fully aware of, the solitonic potential. And it includes self-interaction terms of fourth and sixth order in this particular form. One thing that is very nice about this is that it allows you to construct, depending on this parameter sigma, that's a free parameter, a very wide range of boson star models with various degrees of compactness. They can even have light rings. And the mini boson star limit is recovered in the limit where sigma goes to infinity. Now, if you want to compute equilibrium models, you make this ansatz. There's no guarantee that this ansatz will work, but it does work. So you assume that you have a time-dependent scalar field, but in a form such that the energy momentum tensor is time independent. Hence, you get equilibrium solutions. And you separate into a harmonic time dependence and a radially dependent amplitude profile. And if you do that, you have effectively a Sturm-Liouville problem with, it's an eigenvalue problem for values of omega. And you get an infinite number of solutions with frequencies omega 0, omega 1, omega 2, and so on. The omegas are increasing. And the index actually gives you the number of zero crossings in this A of R function. The omega 0 is the ground state, and all the states with zero crossings, they're excited states. They're actually all unstable. We don't care about them. They play no role in this talk. It'll be ground states only. And here's an example. This is the famous Kalb limit. That is the maximum mass model for a mini boson star potential. So this is the amplitude of the scalar field as a function of radius, origin, well, infinity. And you find effectively an exponentially decaying potential. This is the mass function. So the mass and the origin is zero because you don't have a singularity. And then as you go outwards, the mass increases and levels off at a constant value. The scalar field formally extends to infinity, but with the exponential fall off, you at round of precision, nothing's happening here anymore. And basically, all ground state boson star models look qualitatively like this. There are important quantitative differences, but qualitatively, kind of a Gaussian of some width, and the mass function looks like a smoothed out Heaviside function. If you have ever computed Tolman, Oppenheimer, Volkov stars, which are the simplest class of neutron star models, you will have noticed a lot of similarity at this point. And this actually holds even for computing entire families of models. So you have your equilibrium models, and for a given potential function, you obtain a one parameter family of solutions. And the most common way to parameterize this family of solutions is the central scalar field amplitude. So if we go back, it's this value here. Here it's well, something like zero point zero 0.07. Uh, well, I haven't got the value here, but it's something like 0.076 or something. And for each value here, you get one boson star model. And then you can display them in a mass radius diagram, as is commonly done for neutron star models. Let's first consider the mini boson star case. So that's the black curve here. The radius defined here as containing 99% of the mass, and upwards you have the mass of the boson star, and every point on this curve is one boson star model. It's one equilibrium model. And if you've ever computed the Thurman, Oppenheimer, Volkov stars, they look the same, virtually. You pick a different potential or you get a different curve. So the potential is effectively an equation of state for your scalar field. And the red one is the solitonic potential with sigma equal 0.2. This looks a little different, but qualitatively, they, they're virtually, they're very, very similar. So I've marked here one particular model, the green one, which will play a role later on. And if you do perturbative analysis of radial perturbations to your boson star model, you find, again, a complete analogy to neutron star models, that the models with large radius are stable. So the right branch here is stable. Then you have the maximum mass model, where one of your radio oscillation modes becomes stationary, and the models to the left are unstable. Virtually the same happens for boson stars, although if you choose more crazy potential functions, the stability curves become more complicated. But that's not the subject of our talk. So we are working with predominantly with this model here, which, as you see, it's to the right of the stable model. So it's of the maximum mass model. It's stable, but it's a fairly compact boson star. Compactness 0.2. I'm not going to say anything about spinning boson stars. There are people in the audience who know more about it than I do. And we exclusively consider equilibrium boson star models that are non-rotating. Spinning boson stars have quantized angular momentum, and there's still probably some debate going on how many of them are stable or unstable, how you form them, and so on. It's a very, very interesting subject, but not in the next 45 minutes. The second background topic, basically unrelated to boson stars, that I want to mention because it's important, is how gravitational wave detection and parameter estimation actually works in practice. I'm not going to go into any technical details here, but I will work with analogies. So the first thing that LIGO analysis people usually do is they search for excess in the SNR of the detector. So the detectors have a background noise, and they try to identify where in the data stream do we have something additional. And they check, is it a glitch? Is it, somebody kicked the detector or so? Or once they rule that out, then they can use more sophisticated analysis of the corresponding data segments. The main method to really characterize the sources is called matched filtering. And I like to compare that with the search or the analysis of a fingerprint on a crime scene. So imagine you're on a crime scene, you've got a fingerprint, and well, the fingerprint on its own is worthless. What you need to have is a catalog of fingerprints of potential culprits. And then you throw on your computer, or in the past people did it by eye, and then you find a match, and that's your solution. Now, this is idealized. Gravitational wave data analysis doesn't quite work like that because the fingerprints are blurred. So the fingerprint is not a pristine, clean fingerprint. Somebody smeared over it, which reflects the noise that we have in the data stream. In the data stream, and we'll see examples, you do not only have the signal, you've got a lot of background noise. So the fingerprint is blurred. So you use suppose I have a database of all your fingerprints, and I have a fingerprint, and then I end up with a probability distribution across the parameter space. And sorry for that, you're the parameters. And I end up with, well, 50% chance it was me, it was Uli, or 20% it was Carlos, 10% it was Antonio, and so on across all of you. Each of you gets a probability assigned with them. And that's the result that LIGO reports. And instead of having the probability distribution across U, they have the probability distribution across the parameter space, masses, spins, luminosity distance, sky location, anything. So that's why you always end up with probability distributions. And one thing I would like to highlight is that at the moment we really have comprehensive fingerprint databases only for black holes in GR. People have simulated other systems, but there are nowhere near enough simulations and accurate simulations available to construct a full-blown approximate, which effectively has to provide a theoretical prediction for the expected signal at every point in the parameter space. This is a very, very difficult and challenging task. It's very, very hard, and black holes are the best understood system in GR, and therefore we have good fingerprint database for black holes in GR. For the inspire part with post-Newtonian methods and possibly EOB, you can do something reasonable for neutron stars, but the merger part of neutron stars is way too complicated at this point to have any reliable approximates. And that, of course, creates a problem, because let's assume that the fingerprint I've collected here actually doesn't belong to any of you, it belongs to someone else who's not here, and I haven't got a fingerprint database. Or I like to use the example, say it belongs to a chimpanzee. We haven't got fingerprint databases for chimpanzees. And the chimpanzee is, of course, say it's a boson star or a black hole in modified gravity and so on. We will use the approximate we have, the fingerprint database, and I will still conclude it was Carlos, even though he's totally innocent. So that's a bad thing, and it's a serious scare. At the moment, we are a hammer, because the only thing we have are nails. So we shouldn't be surprised that everything we see is a black hole in GR, except for the few cases where we know from the mass range there's no way this can be a black hole. So it's a neutron star. But we are potentially biased, severely biased, because we don't have theoretical data for anything else. Okay, so what are the parameters that we're thinking of? Well, it's the standard parameters you have for any compact binary. These are the standard black hole parameters. You have the masses, spins, eccentricity, which we usually sweep under the rug, although this is starting to change. And then we have the so-called extrinsic parameters, which are not a property of the actual black holes or other compact objects, but they are a feature of where the hell they are relative to us in the sky. It's the right ascension, the inclination of the orbit, polarization, the time when the signal comes, and so on. This is a massive problem because we're already here at what, 15 or 16 parameters, and a 15 or 16 dimensional parameter space is damn hard to theoretically cover, especially if you have to do numerical relativity simulations. I'm not going to go into the details of the tools people use to create approximates. It's a very, very challenging tool, and people have invented very sophisticated methods ranging from PN and EOB to surrogate models, machine learning ideas, and so on. But there's still a lot more work to do on this, even for black holes. For our boson stars, we have the following additional parameters. The potential parameter sigma, which I have already mentioned. A scalar phase parameter. If you have one boson star, it doesn't matter whether you change the phase by pi or any non-zero multiple of pi, it's the same star virtually. But if you have a binary, this makes a big difference. And one of the stars may actually be an anti-boson star. That means the complex scalar field rotates the opposite direction in the complex plane relative to its companion. Also makes a big difference. So here's the motivation for our specific project. So ultimately, the long-term goals are to test the nature of compact objects, because if we really want to seriously identify, wow, this is a boson star, either we need a smoking gun effect, or we need a statistically significant preference of a boson star model relative to a black hole model in the sense of Bayesian statistics. And for that purpose, of course, we need a proper template bank for boson stars. So this is the first step of trying to construct something like that. Well, the scalar fields we are considering here are in the range of 10 to the minus 11 to 10 to the minus 20 electron volt. It's a funny feature of boson stars. The lighter the scalar field, the more massive the boson star actually is. Um, Boson stars are really, really exciting for various reasons. One is that they have a vast range of compactness, and it's not even fully known whether they might even exceed the Buchdahl limit. I don't think they do, but they might. But they will definitely go well above neutron star compactness, so they can have light rings. They can have any mass. So if you do the modeling, you're essentially covering LISA modeling, LIGO modeling, all in one go. They are very amenable to numerical simulations because they don't have singularities. They're perfectly smooth, but they have no shocks. They have no curvature singularities. They have no surfaces. They're numerically very amenable. And of course, that's the reason why I like to regard them as proxies for something that is not a black hole. So here's the set of immediate questions we want to answer and how we're going to go about. So the first thing is actually we would like to know, suppose a boson star binary goes off in the universe, would LIGO see it? If yes, what would LIGO tell us about the source? And then, from a more theoretical point of view, how good is our numerical modeling of boson stars? Can we do it at the level of accuracy as we need to do, which basically means can we do it as well as for black holes? So the first thing, of course, is to address the last question, where you have to sit down, write a code, and run it. And during the 6 months, if you have no admin work, then you can go on vacation until your simulations are finished. Um, then we have our waveforms. We have to calibrate the accuracy, do convergence analysis, the whole enchilada. You have to do numerical relativity. But that's basically what we've done. Then you take your waveforms, you inject them into the LIGO detector noise. You can do that with the infrastructure provided, for instance, by the Bilby tool. And then you analyze them. You inject signal after signal after signal. We injected hundreds of signals. And you analyze the parameter estimation that this injection gives you. And you can do a test of GR. The test we focused on is the simplest test. It's to check for the residuals. You will see later on how this works. So I don't need to spend time on this. So if you're interested in the modeling, I don't want to spend much time on this, but here is the rough summary, the 10-second version. We have the action. That's the action I already had on the earlier slide. Gives you the Einstein-Klein-Gordon equations. We formulate that in the CCZ4 for the conformal Z4 formalism. Following the version of ALIC, there's an alternative version from with David Hilditch and colleagues. I think they both work equally well. So we tossed a coin and picked that one. We use two numerical relativity codes for comparison purposes, GR Chombo and the lean code I'm working with. Technical details, resolutions here are in units of, roughly speaking, the total mass, 1/48 to 1/32. So domain size, we use 8 refinement levels. If you've done black holes, this is a comparatively coarse resolution by black hole standards, which is nice. And it's an immediate consequence that we don't have singularities in boson stars. That's a plus. Okay, then let's see what we get. So here's just a movie. Compact binaries, if you watch the movies, people try and throw all the shenanigans in there, but the fact of the matter of the fact is they're boring. They orbit each other. Yeah. At some point they merge. In this case, I think they form a black hole or a boson star. I've forgotten whether this is the fluffy or the compact one. That's it. So this forms a boson star. I mean, of course, it's still exciting. They emit gravitational radiation, but for a you can describe the behavior to a 3-year-old, and they will get the gist of it, even though not the details. Here's the trajectory, and mainly I'll be focusing on two types of binaries. A17 is compact. That's German for compact. And A147 is German for fluffy, less compact. The numbers are the central scalar field amplitude. D14 and D19 are just it's a bookkeeping measure for the initial separation. Don't worry, they all complete something like 15 to 20 orbits. So this is a compact one, and this is a less compact boson-Stein spiral. And these are the trajectories. So one guy starts here, the other here, and then they go on and on. And but you already see a significant difference here. This guy has much more of a plunge behavior than the compact one. And this has consequences for the gravitational wave signal. Sorry, say again. Oh, for these two examples, they're in phase. Yeah, they will look very different when they have phase offsets. Absolutely. Actually, it's something that we're investigating at the moment. And the differences are, to put it mildly, they are dramatic. So actually, especially for this guy, we have different phases in this talk. And there the effect is less dramatic. So it depends actually on the compactness, how dramatic the phase offset really is. I should say the phase error is ballpark 0.1 to 0.2. That's a combined error from discretization, finite extraction radius, and so on. This is not as good as spectral black hole simulations, but it is as good as everybody other than the SXS collaboration. This is roughly the accuracy finite difference in code set for black hole simulations as of now. The amplitude error is a few percent. Amplitude 3% may sound quite a lot, and yeah, it's not optimal, but the amplitude error is actually far less significant for LIGO analysis. The phase error is really what matters in using waveforms in LIGO. The eccentricity is reduced again to the levels we have for black hole binaries. So the answer to the first question is, by and large, we can do it with the same quality as we can model black holes, which is good. Oh. These are the corresponding signals. This is the strain. So if you use to psi4, the Newman-Penrose scalar, it's integrated twice in time. As a function of time, the top one, if I sold you this as a black hole wave signal, you would buy it. There's no chance by eye you can distinguish that from a black hole binary. Bottom one, you would probably tell that's a bit freaky, especially here at merger. This ain't a black hole. This is the fluffy boson star binary, and this is the compact one. And this merger and ring down part actually plays a key role in the analysis. So the waveform approximants we're going to focus on here are IMR phenom XP. That's the most important one. That's the standard black hole approximant. So it's based on black hole. This approximant assumes you have a black hole source, a black hole binary source. It has quasi-circular binaries. You have spin precession included, and you have quadrupole modes. That means L equal 2. It does not have the higher order modes. There is a version called XPHM, which has higher order modes. Frankly, it doesn't make much of a difference which one you use. The second one includes tidal effects in the spiral phase. I'm not going to spell that out. These guys are pretty crazy in inventing names. It's a frequency domain approximant, again, quasi-circular, spin precessing, neutron star binaries, but the merger phase is not accurately included here. And they incorporate tidal deformation in terms of two parameters. A tidal deformability parameter for constituent A and for constituent B. We've tested way more approximants, doesn't make much of a difference at this point. So, oops. So what we do is we have our numerical signal. And we can scale the mass of the binary by simply changing the value of the scalar field mass from 10 to the minus 11 to 10 to the minus 15 electron volt or whatever value. So in short, just like the Schwarzschild metric is valid for any total mass, one numerical waveform for a boson star binary is valid for any mass. It's just a trivial rescaling you have to do. So we fix this. We also have to fix the extrinsic parameters, well, sky location, inclination, initial phase, the time, and so on. And then we throw it in, we pipe it into Bilby. The only parameters we vary in a significant manner is the total mass and the luminosity distance. But the luminosity distance, we only vary it such that we have more or less the same SNR for different total masses. If you have a very heavy binary at the same distance, it will radiate more strongly. And we just want to compare events with similar SNR. So we move the heavier injections to larger distance. But it's only to keep the SNR roughly the same. The main diagnostics are the recovered masses and spins. We also look at some other parameters, but these are the most important ones. We look at the recovered SNR. Bilby automatically gives you a base factor for saying what's the statistical significance of having an event relative to having nothing but noise in the data stream. And then we can test the residual for compatibility with Gaussian noise. So here's an example. So this is one of our compact boson star binaries in phase with a total mass of 77 solar masses at a luminosity distance of 200 megaparsecs. This is close. It gives you a nice picture. That's why I've chosen that model here. Normally, we would have put that at 500 megaparsecs. But we wanted, for display, I wanted a nice, beautiful picture with high SNR. In this picture, you have time on the horizontal axis, and the whitened strain, that means the LIGO sensitivity is accounted for. LIGO is sensitive in a certain frequency regime. If you're outside of that regime, the signal looks weakened, while because LIGO becomes blind to it. And there are three curves here. The injected signal is hard to see. It's because the blue line and the black dotted line, they're virtually on top of each other here. But trust me, underneath the blue line, there is a black dotted line. That's the injected signal. It's not quite the numerical signal because it has the LIGO sensitivity superimposed on the amplitude. But other than that, besides that, it's the numerical signal. Then the sand-colored or orange or brown-colored one, that's our injection plus data noise, which is a random realization of standard LIGO noise. And of course, you see, this is a high SNR event here that we're simulating. And you see, that's actually quite, even by eye, you see there's something in there, right? If you ignore the blue line here, and there's clearly some pattern superposed on the noise. And then blue is the recovered curve. That's what Bilby tries now to match the brown curve with a black hole waveform. And the best result Bilby comes up with is the blue curve. And you see it's virtually on top of the injection. So you already see in this example by eye that at least for this particular boson star binary, Bilby would happily say, congratulations on your 97th black hole binary. It would not notice that this is a boson star. And these are the parameters with some, I think, the 90% confidence interval. So Bilby thinks that it's a black hole binary with a heavy component of about 38 solar masses, a light one with 25. Of course, this is wrong. We had two equal mass boson stars with 38.5 solar masses. And Bilby thinks it's at 236 megaparsec. That's actually pretty damn good. But Bilby thinks that the heavy one is almost extremely spinning, dimensional spin of 0.95, whereas in reality it is not spinning at all. The lighter one has a small spin. The recovered SNR is almost identical to the injected SNR. That's good, because that means essentially the entire signal has been identified by Bilby, and Bilby does not see a, a significant residual. The residual is the sandy colored curve minus the recovered signal, the blue signal. And the result, of course, should only be noise. And this is what the residual test is doing. It's telling you, in a statistical sense, is the residual compatible with Gaussian noise? And for this case, it is. Now, the key feature, of course, of this example is the parameter estimation is heavily biased. The masses are wrong, the spins are so bad they're not even wrong. So we analyzed that for a large class of injections. So we changed the total mass, and that plays a big role because if you have a low mass binary, then it will have a high frequency. And that means LIGO sees much of the inspirer, but probably not too much of the merger, because the merger gets so high frequency that LIGO becomes blind to it. Likewise, for heavy binaries, LIGO virtually only sees the merger and ring down, and therefore it's virtually a burst signal. This is why the 190521 signal is compatible with anything from a Broca star to a cosmic string to a black eccentric black hole, because it's effectively a burst. It's compatible with virtually anything you analyze. And that, of course, introduces a heavy degeneracy. And who knows, maybe something really exciting is hidden behind that signal. At this point, we don't know. I think the latest analysis is that Bayesian statistics still slightly favor the eccentric binary, but who knows? But that's the cool thing about science. We want to see cool, unexpected things. So in our analysis, we actually proceed in parallel, well, sequentially in two ways. In one case, we tell Bilby that our injection has zero spin. So we don't allow Bilby to depart from zero spin. And the second injection, we repeat the same game, but we say, Bilby, we don't know nothing about the spin. So obviously in the previous example here, since Bilby reported a large spin, we allowed the spins to vary. But we've done the same injection where we told Bilby, no, A1 and A2 are zero. And even then, Bilby is doing a pretty good job recovering the signal. So this plot is, at first glance, it might look simple, but there's a huge amount of information here. How much time do I have left? Oh, 20 minutes. Oh, wow, cool. We might actually make a lot here. Yeah. Great, thank you. So let's focus on the upper left panel here. Ignore the others. If you understand the upper left, you understand them all. The horizontal axis is the total mass of the injected binary. So we've injected, well, not zero, obviously, but 10, 20, 40 solar masses. The example I had was 77. So it was probably something like this guy here. So the horizontal number tells you, that gives you the total mass of the injection. The vertical axis is a normalized version of the diagnostic parameters. The masses M1 and M2 and the spin. Let's start with the spin. That's the easiest one. The spin are the crosses, the red crosses here. And it's not the individual spin, but it is what some people call the effective spin. It's essentially the sum of the spins projected onto the orbital angular momentum. So the orbital angular momentum is always the z-axis for us. And if the spins are pointing downwards, then you measure the z component downwards and you add them together. That's the effective spin. So a negative number means that the spins are effectively anti-aligned or partially anti-aligned. A positive value means they're partially aligned. Due to normalization, this number is between -1 and +1. And you already see all the crosses are below the zero line, which is indicated here for ease of reading by a dotted horizontal line. So we have a preference for anti-aligned spins. Now, obviously, we only get a spin diagnostic if I allow Bilby to vary the spins. So that analysis is in red color. So there are no blue crosses because in the blue case, the spin is 0 because we tell Bilby it's 0. So there's no point in plotting the blue crosses here. They would all be on the 0 axis. The dots here, and sorry, no ice cream if you guessed that, they are the masses M1 and M2. And bear in mind, these are the masses that Bilby reports to us. They are not the masses that we really injected. Bilby always thinks we have unequal mass binaries. Well, that's because equal masses is a set of measure 0 in the parameter space. So the big dot or the big red circle is the heavy mass that Bilby thinks it finds for the injection where we allow the spin to vary. The little red circle is the mass that Bilby identifies for the smaller companion. So trivially, the small red circle is always below the big red circle. At best, they can be at the same location. Now, I've normalized them, these values, with the individual boson star mass of each of our binary components that we injected. So if a circle is right on the horizontal line at 1, then it means Bilby has found exactly the mass that we injected. Now, of course, it hardly ever does so. But you notice the big red circles, they're actually reasonably close to the injected value. So Bilby, for some reason, is doing a pretty damn good job with the massive, with what it thinks is the massive member of our binary, but it's not so good with the lighter one. The blue circles are the results that you obtain if you force the spin to be 0. Okay, so we inject the signal twice. Once force Bilby to conclude that there's no spin, then it gives us the blue results. And you see, the blue results are always worse. They're farther apart. The heavy one is way too heavy and the light one is way too light. And we can understand why Bilby concludes that. We come to that a little later on. So in the upper panel here, we conclude if we force the spin to 0, Bilby thinks that the binary is much more unequal mass than it really is. So there's a preference here for Bilby believing that it is an unequal mass binary. If we allow the spin to vary, then Bilby still doesn't arrive at equal mass binary, but is much better at arriving at a fairly unit mass ratio. However, it systematically identifies anti-aligned spins. And now the other panels are the corresponding results for the other binaries. And you see they're different. So let me first look at the bottom left panel. This is the same binary, but here one of the stars is actually an antiboson star. And this is the best injection we can give Bilby. You see, the spins are very, very close to 0. The masses, except for the very, very high end of the total mass, they're reasonably close to unity. And we will look at the wave signals in a moment and see that indeed the boson star anti-boson star case has the most similarity with the black hole binary. This is the fluffy one we come to later on. This is the antiphase binary. So here one of the boson stars is dephased. Don't confuse that with anti-boson star. Anti-boson star means that the frequency is negative. Antiphase means you just add pi to one of the star's phases. And you see here, if you compare it with the top left panel, it's almost the other way around. For this binary, Bilby is pretty good at finding the correct masses if it accepts the spins are 0. But when the spins are allowed to be non-zero, then the masses are dramatically different. And now Bilby prefers aligned spins. For the fluffy binary, that's in a way the simplest case. It's all over the place. It's a Russian salad of parameter estimation. This is because here Bilby has the hardest time to identify it with the black hole binary. So here's a more in-depth analysis of the fact that the anti-boson star binary does so well. This is a corner plot. If you've never seen a corner plot, fall asleep for 1 minute. If you know what they are, this is the Q is the mass ratio, m1 over m2, that's between 0 and 1. M tot is the total mass, dl is the luminosity distance, and chi f is this effective spin I've mentioned. And this is the projected probability distribution in the plane, mass ratio versus effective spin, and mass ratio versus luminosity distance, and so on. The kind of brownish horizontal and vertical lines, they are the injected values. So you would, ideally, your recovered probability function is on top of the brown line. And the two cases here are in blue for the anti-boson star binary. And you see, that's a pretty good agreement with the injection here. That one too. Whereas the regular boson star binary, that's off. It's basically incompatible statistically with the injected values. So somehow, well, here even the anti-boson star case doesn't quite match the total mass, which is up here, but it's much better than the regular boson star binary. Well, why is this the case? And the key answer is the chirp strength. What do I mean with that? Um, well, maybe I should jump ahead by one slide. This plot, it looks more complicated than it really is. This is the numerical signal. Horizontal axis is just time, and the vertical axis is the gravitational wave amplitude that comes out of the numerical simulation. There's no observational crap here. Let's start with the black line. The black line is the bottom one here. That's for the regular standard boson star binary. Then we have the top curve is actually the antiphase boson star binary. So you see this is more shallow. The black line starts off weak and then rises very dramatically. We call that a steep chirp. Whereas the bluish curves here, they have a shallow chirp. They already have a large amplitude here, and it doesn't rise very dramatically. The black hole equal mass black hole binary is actually this reddish curve in the middle. So you see the boson star binaries, depending on their phase offset, they're kind of straddling the black hole chirp. The blue one is the anti-boson star binary, and if you ignore this oscillatory pattern for the moment, you see it's virtually on top of the black hole binary. That's the reason why Bilby is very good at identifying anti-boson star binaries with black hole binaries. They have virtually identical chirp strength. Now, going back to black holes, now we have to understand how does the chirp strength vary across the black hole parameter space. So let's start with non-spinning black hole binaries. Forget about boson stars for the moment. These are results the numerical relativity community has accumulated over the past 20 years. Equal mass binaries have a shallow chirp, whereas unequal mass binaries have a steep chirp. And this is easy to imagine if you think of an emery. An extreme mass ratio binary, it's basically a test particle orbiting a big black hole. And it's almost on geodesics. So it orbits and orbits and orbits, no inspirer whatsoever. Then if you add Selphos calculations, you have a little bit of an inspirer. But once it reaches the ISCO, it suddenly plunges in. So that means you have a very dramatic rise, or from your side, it looks like there's a virtually constant amplitude and then plunge. So it's almost a Heaviside function. Whereas equal mass black hole binaries have a much smoother inspiral. So this is something important to bear in mind. When our boson star binary has a shallow chirp, it favors equal mass black hole binaries. And if we have a steep chirp, we favor unequal mass binaries. Later on, in particular, the group from Rochester studied the effect of aligned and anti-aligned spins. And they actually found that the chirp strength, as well as a bunch of other properties, like the total radiated energy, depends strongly on whether you have an preferably anti-aligned spins or aligned spins, the so-called orbital hang-up. So if you have aligned spins, the chirp is shallow because it's effectively the vast amount of angular momentum you have in the system, and GR doesn't want you to form a naked singularity. So the binary spends more time orbiting each other, radiating away angular momentum, and that results in a shallow chirp. Whereas if you have anti-aligned spins, they're quite eager. They plunge pretty quickly. In numerical relativity, this is a fairly well-known result. Post-Newtonian people find the same thing. So this is something else to bear in mind. If we have a shallow chirp, bear in mind, Bilby thinks we'll only have black holes. It will conclude we likely have aligned spins. And for a steep chirp, Bilby will conclude the spins are anti-aligned. And the rest is actually just piecing all of this together. And we start with the regular BS binary. Bear in mind, that's the bottom black curve. That's a steep chirp. Okay. And now Bilby, of course, thinks it's a black hole. So inside the black hole parameter space, Bilby would try and look for something that has a steep chirp. And as we have just seen, there are two ways of getting that. Unequal masses, anti-aligned spins. That's this panel here. So let's look at that. And this, of course, is exactly what happens. If we allow Bilby to vary the spins, Bilby finds anti-aligned spins. If we don't allow Bilby to vary the spins, then it has to resort to pretty high unequal masses. Very, very different mass, very, very small mass ratio because it's very, very much below 1. And this is, whereas if you allow Bilby to vary the spins, well, some of this deviation from a normal black hole binary can be outsourced to the spin, and then Bilby does not need to resort to unequal masses as heavily as before. So in consequence, this is what Bilby finds. Oh, yeah, it's a black hole binary, all right. But yeah, anti-aligned spins, unequal masses. And then we have the opposite case for the defaced, because a very well-known effect that has been known for at least 15 years is that antiphase boson stars, they repel each other. So they delay the inspiral, the merger phase. So that's why they have a shallow plunge. A shallow chirp. Sorry for that. And well, it's just the opposite. Bilby now has to find a way in the black hole parameter space to obtain a shallow chirp. Well, if we force the spins to be zero, the only thing Bilby really can do is to go to as equal masses as possible. And that's why here the mass ratios is virtually 1 for all these cases. If you allow Bilby to vary the spins, well, Bilby will conclude, oh yeah, they are aligned. They're preferably pointing in the same direction because they have a shallow chirp. And then you have the case of the anti-boson star binary. Well, Bilby says, oh, these oscillations, they're crazy, but I think you're just an idiot modeling or observing things. So I ignore these oscillations. Oh, that's a pretty damn good black hole binary of pretty much no spin and equal masses. And this is exactly what Bilby reports. Now, obviously, this will deteriorate when you go to either very low or to very high masses. At very high masses, you only have a burst signal. Bilby cannot really see anything of the chirp because it's just a burst. And if you have too small mass, total mass, then Bilby only sees the earlier part of the inspirer and it doesn't really see the late inspirer and merger. So then the parameter estimation gets a bit creepy. But that's just something we have to live with. Okay, and finally, how about the fluffy boson star binaries? And effectively, we can define fluffy boson star binaries as boson stars that do not form a black hole at merger. They're not compact enough to have a black hole as the merger remnant. And we have already seen that the merger and ring down signal look pretty different from what we know for black holes. And indeed, Bilby confirms that. So here's an injection. It's very similar to the plot I showed you earlier on for the 77 mass compact, solar mass compact binary injection. Again, here we have the black curve, which actually looks a little reddish here from my point of view. The blue is the recovered signal, and then brown is always injection plus noise. And here you see that's not a particularly good match, especially the Inspira is lousy. I mean, the amplitude is totally off, even the phase isn't perfect. The merger part, pretty okay. And then the ring down, wow, that sucks. This is the same thing, but now injected with a very low mass. The total mass here is now 5 solar masses. So we have 2 boson stars, each with 2.5 solar masses. We put it at a much smaller distance, so we have the same SNR. And then LIGO, of course, is very good at seeing the Inspira. It sees something in merger, but it's already pretty contaminated because LIGO is much noisier, has much more noise there. And here you see that the Bilby's recovery is a pretty damn good match for the Inspira, but it's total crap at merger. And this is what we uniformly find for injections of the fluffy boson star binaries. The black hole approximants, they either capture the Inspira or the merger, but never both and never the ring node. And these cases leave behind a Gaussian a residue which is definitely not compatible with Gaussian noise. So if LIGO sees such an event and identifies, no, there's a significant residue here, that would be a strong indication that we've seen something that's not a black hole in GR. That doesn't mean it's a boson star, but something else. Okay, let's conclude. So remember the 3 questions we've answered and asked. Here are the answers. Yes, we can. We can simulate both boson star binaries at the same level, I think, as black hole binaries. LIGO would quite comfortably find boson star binaries. And for compact boson star binaries, Bilby would actually happily report, yeah, it's a black hole binary. However, the parameters are heavily biased. Obviously, that's something you wouldn't notice in a LIGO analysis because you don't know the injected parameters, because you don't know the true source. But if we see something that we think is a boson star, we recover it with a black hole approximant, we shouldn't trust the parameters all that much. But compact boson stars look very, very similar to black hole binaries, whereas fluffy boson star binaries have more characteristic signatures. And obviously, there are lots of things that we haven't done yet. So we hope, and for some cases we already know from the simulations we're already doing, there are other parameters that we can vary in the boson star binary systems that result in pretty clear-cut smoking gun signatures that hopefully would be more easily distinguishable from black hole binaries. But this requires a lot of work. These simulations are very, very long. You have to make sure you have the right accuracy. You might require higher resolution and all that. It's a non-trivial task, but still, boson stars are a pretty nice candidate thing. And if I compare that with neutron stars, I'm glad people are doing neutron stars out there, and I'm not, because neutron stars are, for those of you who have done them, they know they're very, very challenging. In comparison, I think boson stars are easier. Right thing for me. Obviously, we need to cover the parameter space and identify a good strategy. That requires a lot of work because we have yet to identify what the characteristic signatures of boson star waveforms are, especially in Fourier space. There will be bumps in the power spectrum, and these things we do not yet fully understand. And then, of course, we need to identify efficient tools for analyzing gravitational wave observations using BS templates. Well, thank you. I hope I haven't overrun too much.
Okay, now with this technological improvement for a faster or more efficient question and answers, so Carlos first.
Uli, thank you very much for the beautiful talk. You guys are really doing wonderful work, and it's really clear and the way forward. My question is related to your conclusion or your statement about compact binary boson stars look very similar to binary black holes. But of course, in the case of the binary boson stars, we have at least one extra degree of freedom, which is this relative phase. So even for the very same binary, the same two boson stars for which you see the similarity, if now we explore that extra parameter, the phase difference, you might get qualitatively very different features like a bouncing behavior. So even in the in spiral, there could be qualitative important differences.
Yeah.
So it's not only the compactness, it even defining completely the model, kind of choosing whatever masses you'd like to have, which you can vary by varying the boson mass. Of course, this gives you this extra, I don't know if it's opportunity or difficulty, but I would like to know your thoughts about that. Thank you very much.
So, and in fact, the latest things that we showed. The answer is
The simple answer is yes. So for the compact boson stars, the effect of the defacing seems to be very, very subtle, basically what I've shown. However, this totally changes when you go to fluffy boson stars. And I'm giving away some results here, but uh, it took me, I think, 6 months to simulate this. Let's see, I hope I found the right directory. Yeah, that's the gravitational wave signal of a defaced, antiphased fluffy binary. And I don't know if you can, well, you can't read that. I've simulated that for 50,000 amp. Yeah. Of course, by that time, this is a fairly low resolution one. I've picked up roughly one full cycle of phase error. But you see, the early stages look very, very similar. And then you have a floating orbit. And if I show you the trajectory, this is the trajectory. Don't scoop me on this. My collaborators will kill me. But this is the trajectory. No, but in a certain way you have,
Yeah,
because you've seen it in head-on collisions, I'm
yeah,
sure.
yeah, we have.
And this
Yeah,
is exactly what happens here.
yeah.
However, and that is a very important point, which in some ways a blessing and in another sense is a curse. This is only happening if you have perfectly equal mass. The moment you deviate from in the mass ratio, even by a tiny little amount, you see what's happening. The frequencies are different.
Mhm.
And that means that your phase difference is a function of time. And that means that you cannot longer have this perfect floatiness
Mm,
because the scalar field offset will be pi at some point, but it will be zero half an orbit later.
I see.
And then they will merge after all. Although that's something we have only very, very superficially studied. Unequal mass boson star binaries have the unequal mass case in a certain way has a democratic effect on the defacing.
Hmm.
Because the initial defacing in the end, it doesn't really matter. What really matters is the defacing at merger, and that is even a time-dependent function. However, from the few simulations we have, and they are unfortunately a good deal harder. I'm a little annoyed by the fact that unequal mass boson star binaries are. It's not just, oh yeah, just change the mass ratio and you're done. You have to do a little bit more to get results of comparable quality. And initially, the results looked totally weird, and I thought, wait, what the hell is going on here? But then gradually we started understanding, of course, the phase offset now is time depending, and this has significant repercussions on the signal, which could be quite complicated to model.
Right. Well, if you allow me, Ulu, but wouldn't that apply also to the compact case? So couldn't it be that even in the compact case, when you get close to merger, you have an opposite phase? Because this is what we
It
see in
does.
head-on, and therefore you could even get a very qualitative difference in that case as well.
Yeah,
Yeah.
absolutely. This can happen. If they are so compact that they easily form a black hole at merger, then it doesn't matter very much because once a horizon forms, the
Yeah.
scalar self interaction stops
Right.
doing much.
Right.
However, the weirdest simulation actually is the anti-boson star case, and that's something I do not yet fully understand how the hell this can happen. If you look at the animation of that, what happens is initially they spiral just like they always do. Then they merge, and you have a total mess of a scalar field distribution. This is for the fluffy case, not for the compact anti-boson
Okay.
star case, because that forms the black hole, end of story. But in the fluffy case, you have a total mess, and then gradually this mess reassembles itself into two boson stars that separate like this on a straight line. It almost looks like in the information paradox. How the hell can it happen? I mean, in some sense, the boson stars, despite the violent, complex, and messy merger phenomenology, they preserve in a way their information that they actually have been originally created out of two orderly, separate, self respecting boson stars, and they're capable of reassembling.
Mm,
And then they just, because they've lost most of the angular momentum, then they more or less
I see.
depart on a. There's a lot of really potentially crazy phenomenology going on. I don't think we understand all of it yet, and we probably still have a lot of other things to see and identify.
Okay. Thank you very much,
But
Uli.
this is the really cool thing about boson stars. They are deceptively simple mathematically. It's just a scalar field, a potential function. The phenomenology they have is breathtakingly complicated, which is again a reason why I think they're really cool as proxies for plenty of other systems.
Yeah. Thank you. I definitely agree with that. Yeah.
I know I'm running in open doors here.
I have a naive question. When you were showing the gravitational wave from the fluffy binary, that resembles somehow the merger of neutron stars that go to prompt collapse.
Yeah.
So I'm wondering if we can somehow change the parameters or rescale the parameters in order to see or to identify this binary as a binary neutron star.
I've had similar thoughts because I agree. I've seen some neutron star papers where people showed waveforms, and I thought, wow, this part, and you see it better in the insert here. Here you see it.
Yep.
That's the ring down. That is reminiscent of some neutron star simulations, at least qualitatively. Of course, there are other neutron star simulations that look different, but that depends on the parameters. It's a good question. I I think this is worth investigating. I don't think I have the time to investigate that myself, but I think it may be a very interesting avenue to explore to what extent you might actually use boson star waveforms to approximate neutron star waveforms. Because the one thing they clearly have in common is that the end product, if it's not a vanilla black hole, is a bunch of debris floating around. And you don't gravitational waves don't care too much about what that matter is made of. And either for comparison, how different are neutron star and boson stars, um, or can we use the combined information to create approximants that sort of capture both aspects? I think it's a very interesting and valuable question.
That's
We still have some constraints there. Okay. So thank you, Uli, for the very nice talk. I was really excited by your words. So
Thanks.
I asked the same, more or less the same question at one of the seminars before you on Monday. It was about the environmental effects. I know that you've been working in this for a while, And particularly for the boson star case, we do have that, right? We do have like, you are not in vacuum, you have these scalar fields. And I was wondering if you have a way to track of how much energy from these binaries are going through like dipolar waves or even quadrupolar
You mean
waves
scalar radiation?
in the scalar channel, because
Yeah.
these, at least in the perturbative regime, what we've been seeing is that this can be a huge part of that is a huge part of your of that in what controlling your evolution of your binary, right?
Yeah.
So because in actually this dominates over gravitational wave emissions. Do you have any words on that?
So for the, I haven't got the numbers in my head, but if you do a balanced argument comparing the total initial mass with the final black hole mass plus radiated energy, there isn't much left for scalar radiation. But I suspect that this is a very sensitive function
Hmm.
of the compactness. So for the compact binaries that we're doing, I think there's not much hope for the scalar field to escape. But if as you go to fluffier binaries, very likely it's going to happen. And you also have to bear in mind that we still have a comparatively high degree of symmetry here, with the mass ratio uh, being equal to 1. For unequal mass ratios, I can imagine that the asymmetry gives much broader scope for scalar emission. And that is something we have. I would personally favor first studying this in head-on collisions,
Yeah.
and but we haven't done that yet.
Yeah, one thing that I found in these plots that you are showing right now, actually, is that I have very similar plots, but considering just as I said, a perturbative regime, and for the fluffy case, which is less compact, right? One remarkable fact that happens ring down like signal like that one is because we have an absence of the dipolar emission. Basically, the frequencies that are involved in the spiral
Yeah.
phase are not enough to excite dipolar scalar radiation, and these can lead to slower evolutions of your binary. So that's why I thought that maybe there is something going on that. So in one case you could have quadrupolar only, and in the other you could have dipolar, and so on. And
We
also,
have not analyzed that in detail. It's
okay,
something we probably should do. Um, because in principle well, I've only coded up for a real scalar field, but it shouldn't be hard to generalize that to complex one
I see.
to effectively measure the equivalent of the
Mm,
gravitational waveform for scalar radiation. It's a good question. Now, fluffy, of course, is relative, and what I call
yeah,
fluffy zero point 0.1 is an zero point 0.1 compactness. That's pretty damn compact for a human.
yeah, I see.
But um, this is roughly neutron star level.
Mm,
So I think around the compactness, we're starting to enter the regime where some things like what you're saying could happen. For the high compactness zero point 0.2, I think they are too compact to really have much potential for such effects. But zero point 0.1 and lower, definitely. Distinct possibility.
mm. So and the plot that you showed so that one with so this one, no, the one that you showed that you open it in an external so you open the terminal to show an additional
Oh,
plot.
yeah.
So
Yes.
can you explain again? So this is for the given phase, right? Just to show the difference between
The trajectory, it
the
doesn't matter because
and in the waveform.
the waveform, yeah.
Yeah. So this one, so I have, as I say to you, I can show you later. So I have one plot that looks remarkable as that one, but if I don't consider like the scalar radiation at all, if you consider that your evolution is just driven by the gravitational wave, what happens is something very similar to that. So I was wondering whether this phase choice is like constraining a little bit of how much your scalar fields communicate to each other, and then yeah,
There is a paper by Palenzuela, Lena, a couple of others, and
yeah,
almost certainly it's not the only one, where they interpret the phasing effect in terms of an additional energy contribution when the scalar fields overlap. And there
Mm.
you can quite easily see that a phase offset of pi
Okay.
has a negative contribution. And in head-on collisions, people have already realized that they collide like snooker balls. They
Yeah, yeah, yeah.
collide, end of story. No merger, no overlap, nothing. And this is effectively the rotational equivalent. My suspicion, I mean, after 50,000 M, I just got tired of running
I
this.
see. Yeah.
And my suspicion of what this guy is doing, but I'm only conjecturing here. I have no proof, nor numerical evidence for that. But my suspicion is that they will keep orbiting slower, more and more slowly, radiate away all the angular momentum, and in the end, I think they will have the same end state as the head-on collision. They would just slow
Yeah.
down, and then that's the end of it. This is, of course, pointing in that direction without really being particularly strong evidence. Um, so the phasing effect is already known from quite some time ago to have precisely this effect, that they effectively stop the boson stars from overlapping. Likewise, what we've seen in the boson star anti-boson star case, or they merge and then they separate. This also has been found in a more simplified case for the head-on collisions where they just pass through each other.
Yeah.
What I find really astonishing is that in the head-on case, yeah, this is like two waves passing through each other. You can kind of understand it. But in the merger, in the inspiral, the merger is such a complete mess of garbage that you have a hard time. How the hell can you reassemble two clean boson stars out of that? But they can. Um, but the effect of the defacing is reasonably well understood. Recently, we've discovered something for not totally defaced that gave us a harder time to understand it. But I think Tamara has identified what's happening there. But that we need to explore a little bit more. We also need to do some uh, test simulations. There were certainly some rather unexpected features in the inspirals, which initially we thought were numerical error.
All
But
right.
it looks increasingly likely, bloody hell, that's real. But that's, I don't want to say anything because that might still be totally wrong. I don't know.
Okay. Thank you.
Well, actually, just to make a small comment, and Gabriele showed some very nice simulations of the cases that he has been doing with binaries of Procus stars, with Nico and Tony, and you see a bounce clearly. You know, like the case you're talking about, the head-on collisions. We've looked into that, which is much more pronounced in the solitonic case, but you can even see it at the level of the mini boson stars if they are compact enough. But in case with the orbital angular momentum, you can also see they approach and there's a kind of a bounce, and so there's a clear phase impact in
Trouble
that case.
is, we've also seen this bounce numerically for cases where it should not happen. So, where it was clearly a numerical artifact.
Okay,
So that is effectively, we've seen similar bounces,
right.
and we were starting to be suspicious. Is this real or not? So we are doing the test runs now, using
Okay.
different codes, varying a few parameters, gauge parameters, and all that. Initially, I thought, yeah, that's numerical error. Damn it. But I'm moving in the right, more positive or optimistic
Yeah,
direction
and it
now.
makes sense
It makes sense.
because we see it in the head-on
The
as
weird
well.
thing was that initially I didn't understood that we see a distinct asymmetry that didn't make sense to me. But I think actually it does make sense now.
Yeah,
But that's what
we
Tamara
can. Yeah,
has
we
been
can
looking at.
discuss more. Yeah.
But I definitely agree with you that this kind of bouncing behavior is can be very, very
So you would see a sort of
sensible.
anti-chirp also in the signal at
Yeah,
some point, and
yeah.
that would be very
That would
distinctive.
be very cool.
Yeah,
And in parallel, we're in a totally different project. We're analyzing how this looks like in high energy collisions.
that's a different subject.
That's a different animal. Yeah.
In higher dimensions as well,
No,
or
no,
not?
no.
Then we go.
You
Okay.
know, I've the more astrophysically minded
Oh,
people who are very benevolent towards me, people like David and Giro. So I'll say, oh, boson stars. Okay.
okay.
But then boson stars and modified gravity, boson stars and modified gravity in higher dimensions, I think that pushes things too far. No, but seriously, as a mathematical question, I would actually be very intrigued to study boson stars in higher dimensions, not as a physical thing, although it might be relevant to some ADS CFT people. But mathematically, I actually think it's a very interesting question. There must be, I'm surely not the first, there must be solutions. Yeah.
I think it's an open ground.
I
I'm not
mean, we
sure how
could,
motivated it is.
you know,
Maybe, as you say, from ADS-CFT. Yeah.
I mean, you remember that we had sort of 5 to 10 years ago, we had this whole sequence of higher dimensional and high energy collisions. Maybe we should resurrect it for boson stars.
Yeah, yeah,
Just need the manpower.
yeah, yeah. And perhaps in ADS that will be more interesting.
Yeah, yeah, that would definitely be more interesting. Yeah.
Okay, were there more questions? So if not, are there any announcements? Crispin, where is Crispin? It's not here. Ah, there. Any announcement? But before that, let's thank you for the